speaker today is Sagar Vanapalli, and he is a civil engineer. He's working as a researcher since 2016 at Anhalt University in Germany. He's working with Professor Sulphuric, who we just heard from, and he's experienced in FEM in simulations and testing. If you could, please welcome Sagar to the stage.
Thank you. Good morning. I'm Sagar Vanapalli. Thank you for the introduction. Today I'm going to speak about glass and timber lamination. It's a pure indoor application for aesthetic and hygiene requirements. So why do we, motivation? These are some examples of our project partner, and we see most of them are either plastic reinforced or plastic coated or glass coated, and you don't actually see a lot of real wood furniture or wooden structures inside a clinic or a doctor's practice. The reason behind is simple. Of course, even though study shows a positive psychological effect of using wooden environment where the patients are exposed, they show a lower stress levels and also a lower blood pressure on a longer term. A simple example, because wood, when used for cleaning, chemicals react and damage the wood, so we can't use wood in a healthcare center. So what can we do about this? So we thought, why don't we laminate glass on top of the wood? So in that case, the wood is protected from the disinfection, and at the same time, it holds the hygiene standards required from the authorities. So I have a sample with me. If you guys want to see, you can see it later with me. So we used a glass, 4mm glass, anneal glass, and an interlayer of 0.76 thickness everfolia, and we used veneer instead of raw wood, because raw woods have more rough surface and it's hard to laminate. We did some examples on it, but it didn't really work out well. We had a lot of delamination and bubbles. So we used veneer because they're already processed and they're smooth and it's easy to laminate. And we used a wooden board in the back. And the lamination process is similar to a lamination of glass. Instead of one side of the glass, we used the veneer, and it is packed in a vacuum bag, silicone bag, and in a vacuum bag, and heated up to 140 degrees, and it was quite good. We had some positive results. I'll show you some examples. We wanted to develop this panel in 3 stages. The first stage, only the top surface, the top surface was laminated, and the second stage we want to laminate the edges, and the third stage all the surfaces with the glass. But today I'm going to speak only about the first stage, and it's the problems that I faced during the lamination and its durability tests. So we used 6 different types of wood, which was recommended from the project partner because it was widely used in the market. And all the 6 had good lamination effects. I mean, they did produce good lamination apart from large. It had a lot of bubbles, but we'll come to it later. So we'll see some problems, what we faced. First problem, we had cracks in the veneer. This is due to the lamination. The veneer gets dried and also shrinks, and also the interlayer pulls the fibers apart and moves into the veneer. This was one of the reasons, one of the problem. But we tried to compensate with thicker veneer, and we didn't face this problem again. And then bubbles. Although my project partners really liked the example, but we don't want to use this. We can see how nicely how the bubbles orient themselves around the fibers. It was mostly due to not sufficient heat that was developed in the interlayer because the interlayer didn't melt properly. Because when we use the same lamination process for a glass, the glass has better melting system, or the heat transfer is better for a glass rather than wood. So we had to increase the heating time for the lamination, and we did get better options. And sometimes we also had some broken glasses. It was mostly when we had thicker foils. So we also made some tests on 1.52 millimeter glass layers, and mostly all the layers, all the specimens which were laminated with thicker foils tend to break. And then the most important or hard problem that we faced was warping. Warping is nothing but when the wood absorbs or dries water or loses moisture, it tends to bend on one side or the other side. So this was an example where we used thicker foil again, and this you can see that the glass actually broke here too, at the center, because when we use thicker foils, what happens during the lamination is the vacuum bag pushes the corners of the sample, and letting the foil squeeze out more of its layer. And in the center, the foil is still very thick and developing stresses on the glass and making it to break. And similarly, this was a reason in this case, the wood actually bent, losing its moisture, and causing the whole sample to break. The problem with this is all the samples were of 20 by 30 centimeters, and at that level, for 20 centimeters right, it was 2.5 millimeter, so 0.5 millimeter curvature. So when we exploitate and make it for when we make a large scale models like which are of 1 meter size, we would have a wrapping of 2.5 millimeter, which would be hard for manufacturing of joints or any furniture. So how did we solve this? Instead of using the whole wooden sample for lamination, we only laminated the glass with the veneer and later gluing it to the wooden board. This helped us to control the wrapping. And then we check on some durability tests. So since there are no defined DIN, we use the DIN which was used for lamination, for testing the moisture penetration test for the laminating glass. It's done in 2 phases. In the first phase, there's a cyclic test of changing the temperature from minus 18 to 53 degrees, trying to control a constant moisture of more than 95%. And this was done for 1.5 month. That's 56 cycles. 56 cycles, and then keeping the whole sample for constant moisture of 100% at a temperature of 58 degrees. These are some examples of the durability test. And we tested 3 different types of samples. Since in the furniture industry, they usually laminate the glass one side with the veneer and the other side with plastic. So we tested 3 different types. One where all the sides are free, so they're not treated with any plastic, so they're free and they allow moisture penetration. And this type 2, the edges are free, and the bottom side is laminated. All sides are free. And the third, type 3, all the sides are laminated with the plastic. So the results. We tested 36 samples, 2 samples of each wooden type, and out of which 9 samples delaminated, and there was no particular pattern of type 1 or type 2 or type 3 which was laminated, so it doesn't show any effect of the edges. And we should also note that it was an extreme testing for interior application, because minus 18 and 53 degrees are not something that we actually get experience in the indoor. So taking that into consideration, I think the results were quite good for that duration, for durability. I'll show you some examples. This is a before and after. There's no delamination for this specimen, but you see the deterioration of the wood. But that was not our main motive. We just wanted to see the delamination. So this is an example of delamination. One cannot see it perpendicularly, but when bent around, you can actually see the delamination. Apart from this durability test, we also have done some immersion test because we wanted to check if the edges let the moisture to penetrate or not. And since T1 and T2, type 1 and type 2 edges are not at all treated, it is obvious that the moisture would penetrate. So we checked only type 3 samples, each one immersed in disinfection and water for a period of 2 months, and none of the samples actually delaminated. And we see a little bit of deterioration of the wood, but there was no delamination at all. So coming to a conclusion, so these are the first results of our lamination with wood. They seem to be, we did get good results of lamination, and the durability tests also show a good results. So we are moving further with the 2D and 3D lamination. We did have some good results, which we'll be producing it for the next time. Thank you.